If you've ever attended a lecture on group theory or started learning about it, there's a high chance you've heard about the decades-long project in pure mathematics, often called the biggest collaborative research effort in the history of math, the classification of finite simple groups. This video has nothing to do with it, because we are going to classify, or rank, few of the most well-known algebraic groups in a meme tier list. So let's dive in. First, we have the one and only trivial group. So it is the only group with only one element and very fundamental from theoretical perspective. But if we consider it as symmetries of something, it just corresponds to the set of transformations that do nothing. So it can be trivially mapped to D tier. Next, we have the Klein 4 group. It is the smallest non-cyclic group. It has 4 elements on a non-square rectangle or similar shapes. The group actions corresponds to the following: doing nothing, rotating 180 degrees, reflection across the horizontal axis, and reflection across the vertical axis. As it is non-cyclic, no element can generate the whole group. In fact, each non-identity element has order 2. It's a really good first example of a group, especially for beginners learning the basics of group theory. In fact, it can even model the bitwise XOR operation with integers mod 4, which is pretty cool, but let's put it in C tier. The next group is the Rubik's group. Really amazing real-world example of group theory. As the name suggests, it is the group which represents the symmetries of the Rubik's cube. It has exactly these many elements, which is the product of the independent permutations and orientations of the edge and corner pieces of the cube. I will put it in C tier too because only the fun factor carries it. Also, if you want to know more about it, Numberphile has a great video on it. Next, we have the cyclic groups. All these groups are very similar. The Cn cyclic group can be seen as the rotation symmetries of an n-sided regular polygon. For hexagon, these are the 6 rotations which keep it looking the same. Similarly, for any n-sided regular polygon, the corresponding group is Cn, which have n elements. And because it's cyclic, there exists an element of order n, that is, it can generate the whole group. But these have very simple structure, so D tier. Next are the dihedral groups. These are formed when you combine a cyclic group with the 2-cycle or reflection. These also represent symmetries of an n-sided polygon, but along with rotational symmetries, they also include the reflections. So the group Dn has 2n elements. Their structure is a bit intricate than cyclic, so let's put them in C tier. Now the next is alternating groups. I am considering a whole class of groups for these two. It is also nice because otherwise, individually, they have no chance against the infinite groups which are coming up. Alternating group An can represent the even permutations of the set of n elements. For n greater than 4, all An are simple groups, which mean, in some sense, they can't be formed by combining 2 smaller groups. That's cool. They come up in Galois theory too, when discussing roots of polynomials, but interestingly, they also have beautiful connection with geometry. For example, An can be realized as the rotational symmetry group of n-1 dimensional simplex. You may be familiar with a simplex from the simplex algorithm in linear programming. Simplex is a generalization of triangle in 2D to all dimensions. It can also be thought of as smallest n-dimensional shape, like a line segment in 1D, a triangle in 2D, which has A3 as its rotational symmetry group, a tetrahedron in 3D, which has A4 as its rotational symmetry group. So in 4D, we have 4 simplex, which has A5 as its rotational symmetry group. So, B tier. Next are the symmetric groups. These are called symmetric because they also represent the symmetries of simplices. But along with rotations, they also include reflections of simplices. Both An and Sn have very intricate structure, but most intricacy in Sn comes from its An subgroup, so let's keep them in B tier. Next, we have the group of units modulo n, also realized as the multiplicative group mod n. Its size is phi of n, where phi is the Euler's totient function. These groups, along with the cyclic groups, are very popular in computer science community because of their applications in cryptography. All of them are abelian, which means AB and BA are same for group elements A and B. But their structure is highly dependent on n, because they capture the factorization of n, as you might have guessed when I mentioned the Euler's totient function. For example, when n is prime, the group is same as the cyclic group of order n-1. Let's put them in the C tier, because their structure is fairly simple as compared to other groups which we discussed. Let's start with the infinite groups, and leave the last finite group for the last. The modular group, SL2Z, consists of all 2x2 integer matrices with determinant 1. It acts on the complex upper half-plane via Mobius transformations. This seemingly simple action generates modular symmetries, fundamental in number theory, complex analysis, and string theory compactifications. The geometry it defines underlies the modular forms, which appear everywhere, from partition functions in physics to the proof of Fermat's last theorem. When you see hyperbolic tessellations that repeat infinitely, you're looking at SL2Z in action. So we'll keep it in B tier. SO3 is the special orthogonal group in 3 dimensions, the group of all real 3x3 orthogonal matrices with determinant 1. It captures every possible proper rotation in 3-dimensional Euclidean space. Physically, it's the symmetry group of any rigid body free to rotate about an origin, from planets to particles with integer spin. Its structure is non-abelian, and as it's a Lie group, it is topologically equivalent to real projective space, RP3. An n-dimensional real projective space is formed by identifying all points lying on the same line through the origin in Rn+1. As all lines through origin become a point, we get sphere, but only half of it, as the negative directions are also identified with the positive ones. So this is RP2. It is a filled circle with antipodal points identified. By similar analogy, RP3 can be seen as a filled sphere with antipodal points identified. But this space is not simply connected. That's why spin-half particles, like electrons, require its double cover, SU2, for a complete description in quantum mechanics. So let's put it in B tier. Next we have SU2, the special unitary group of degree 2, consists of all 2x2 unitary matrices with determinant 1. It's home to the Pauli matrices, and it governs the transformations of quantum spinors, the mathematical objects describing spin-half particles. In physical terms, SU2 is the double cover of SO3, meaning a 360-degree rotation doesn't return a spinor to its original state. You need 720 degrees. It's a Lie group too, so it's the same as the 3-sphere. It is a 3-dimensional manifold, which is the same as the boundary of 4-dimensional ball. If you want to explore how movement inside a 3-sphere would look like, you can check out this on my GitHub. Moreover, SU2 forms part of the standard model gauge symmetry, describing the weak nuclear interaction. So, A tier. Now we reach the standard model gauge group. This product of Lie groups encodes the fundamental symmetries of all known particle interactions, excluding gravity. SU3, color symmetry, confines quarks into hadrons. SU2 represents the weak isospin symmetry, and the U1 corresponds to hypercharge. This structure is the mathematical skeleton of the universe's quantum fields, so A tier. Next, the E8 Lie group. It is a 248-dimensional continuous symmetry, one of the 5 exceptional simple Lie groups. It's incredibly structured. Its root system has 240 vectors in 8 dimensions, forming a lattice of unparalleled density and symmetry. E8 underlies many grand unified theories in particle physics, and it even appeared in an attempt to unify all fundamental forces, including gravity, in string theory. Beyond physics, the E8 lattice gives the densest known sphere packing in 8 dimensions, and its symmetry group plays roles in algebraic geometry and string theory compactifications. Undeniably, S tier. And now, the Monstre group. It emerged as part of the monumental classification of finite simple groups, the biggest among the 26 sporadic simple group, with a mind-melting but finite order of about 8 times 10 to the 53 elements. The monster appears in the theory of modular functions, vertex operator algebras, and string theory through the legendary discovery known as monstrous moonshine, a mysterious connection between the monster and the modular J function. This bridge between algebra, number theory, and quantum conformal field theory remains one of the most beautiful coincidences in modern mathematics. It has no practical use, but as a pinnacle of abstract symmetry, S tier. That wraps it up. Thanks for watching, and now it's your turn to share your favorite groups in the comments.